Welcome to the new video where we keep going with the ideas of integration, but now we will stop integrating for a second and we'll play with areas under the graphs. This is the introduction of what actually the idea behind integral sign is. Because as you can see on this nice little animation picture, the function has its own derivative and its own integral, right? So we taught you that what derivative means. Here it says slopes of tangent lines, but it's so much more than that. Do you remember the instantaneous rate of change idea of change? That's the most, I would say, exciting one. The change can be so fast. Imagine the Superman changing from Clark Kent to Superman identity so fast that when you blink, he already changed, saved someone and came back, and you never saw that change. So you always keep seeing a Clark Kent in front of you because that's how fast Superman is. In order to capture such a fast change, the limit was created. The limit as time, or space and time, delta t shrinks to 0, right? Then if you hold a camera in front of the Clark Kent and it can make so many pictures in microsecond, you can finally capture him changing. And that's exactly the idea of instantaneous rate of change. Instant change, and you can capture it using limit, even though it's physically maybe impossible. Maybe there is no such a camera, it might not even exist. So then the idea, or the very logical question, then what's the idea behind integration then? If we're undoing differentiation using integration, what does that actually mean? One of the cool ideas that will tell you what it means is that integration is the next level of multiplication. That's a cool idea. I learned about it just recently and I kind of like it. So, when we start teaching kids in school, 2 plus 2 plus 2, right? That's 6, and that's addition. Then we're reaching the next level called multiplication. We say, it's actually too much adding. If you add the same thing, you can just multiply it by 3. That's product, right? And it gives you the same answer. And then the next level was actually to think what happens if multiplications keep being repeated. So 2 times 2 times 2. We said, well, if the product is being repeated, then the next level, the exponential function shows up. That's 2 to the 3. And that's already a different number, and it's much faster, right? Exponential functions and so on. So what happens if you have many, many products, but they're not the same? What if you have 2 times 3 times 7 times -5 and so on? Can you have a faster way to calculate all those products, or you actually have to have a calculator and type in 2 times 3 times 7 times -5 times maybe 2.3? That's very not convenient. It would be convenient to have something like this, some kind of shortcut. And the shortcut is called integration. And that's a mind-blowing idea, which I will try to show you right now through the example of a traveling car. Because people who travel a lot driving, they have this intuition of how distance and velocity correlate. So let's say there's a car traveling at the constant velocity of 60 miles per hour along a straight highway over a 2-hour period. So I was traveling with this constant speed, right? Here's in the graph. Constant speed, we call it velocity here, 60 miles per hour. And I know I was traveling for 2 hours. So how far do I go? You can answer this question right now, but for now I just show you the graph. The graph that's a constant function, right? If this is a function of velocity, here it is, v, with respect to time t, and then we'll call it v of t equals 60. It's written below the line. Velocity function, it's a constant function, and actually it has miles per hour units. Well, I was traveling 60 miles per hour with a speed 60 miles per hour, and I was traveling for 2 hours. How to find displacement or distance, right? Displacement is a positive distance, so you cannot go negatively. Displacement is rate times time, right? So if I was traveling if I was traveling 60 miles per hour and I was traveling I will even write down this way as a fraction per hour, and I was traveling for 2 hours, it will become 120 miles per hour times hour. Hour cancels out, and now I end up to have 120 miles, right? So that means this is my distance. That makes sense. And how did we get it? We get it by multiplying rate and time. How to show it on the graph? Look at the graph, and I'll show you with different color, say blue. On the graph, look at this 2. I took this 2 and multiplied by how high my function is. My function is 60. High, 60, level 60. So I multiplied 2 by 60. Geometrically, what do you see here? What am I making with this blue color? Indeed, I'm making a rectangle. Why? Because the height was 60. The length was 2. 2 times 60 gave me area. What kind of area? Area below the graph of the velocity function. And that's one of the explanations of what integration is. One of the applications is when you integrate this function, and that's going to be in the next videos and in the next chapters, but just for you to understand, one of the applications of integration is integrating this function v of t means find this area below v of t, and that is going to be the same thing. Integral, result of integration, from 0 to 2, and the whole area below this graph. Well, the complication comes in if I'm not traveling with the same speed. And now this is the idea of having different numbers. So when the speed was constant, like over here, 2, and then one more 2, and then one more 2, and one more 2, and one more 2, I can do a shortcut. I can do 2 raised to the 3, right? That's exactly the shortcut here. The speed was constant, so the area is simple. It's just a rectangle. What if speed is different, like I showed over here? 2, then 3, then 7, minus 5. So let me show you how it will look like. 2, then 3. So I was traveling 2 miles per hour. Then I was increasing the speed 3 miles per hour. Then I jumped to 7 miles per hour. Then, in this example, it even became negative for some reason and so on. But just imagine that this is the data. I'm keep traveling with different speed. Now, I cannot create one single rectangle anymore. And this is a very realistic data. So, to find out how far did I go, I still need the same area under all of those green lines. And to find this area, I need to find the area of each rectangle that was created for different speeds. So what happens if speed is not constant? Then I need all of those rectangles. Integration, again, is the shortcut, how to do it faster. And we're going to do it later. And for now, we're going to explain you the idea of approximating the function using rectangles. How to create data out of those speeds. People call it fitting the data or interpolation. They create a function that will lead those numbers I collected from the speedometer, 2 miles per hour, 3 miles per hour, 7 miles per hour, and so on. 2, 3, 7. They create a graph of the function from it, and then they can analyze that function. Find maximum, minimum, can keep up, and finding the area below the function. Very nice example is, again, probably the last example I will do in this series of lectures, using coronavirus in 2020 as a data collection. So we have a data collected as the confirmed cases daily, right? And this is the date. We have 2020, January 23, January 24, January 25, 26, 27. Every day we have number of cases. And that's how data is being created. So when this data is created, it exactly looks like different rectangles. And then you fit this data with this, you see red line, graph of the function. And again, I will mention this again. That's what you call interpolation, extrapolation of the data or fitting the data. You want to fit the data to a nice graph of the function. And this is how it looks like. You saw this before probably, the flattening the curve idea, where we fit the data. Now we have nice looking functions. They look like parabolas actually, concave down. And they're different, depends on if we are strict with sick people, if we are strict with people staying at home or not. So, if I know that from these two graphs, every day this height of this data, of this graph, of the function, tells me how many people they are sick at this concrete date. So how many people are sick? Here is how many people are sick. And this date, it's maximum over here. At this date, earlier, it was few people. That's exactly how exponential function grows, you see? Exponential growth. So, how to find, or I will say this way, what the area below this graph in blue will tell me, all of it, if I find the area below. Just like we had this rectangle for the speed, rectangle for the velocity. That gave me distance, because we had time on the x-axis and velocity on the y-axis, so the area gave me distance. With this case of people being sick, x-axis is time in days, y-axis number of people being sick. The area in blue will give you total amount of sick cases for the total amount of time we're recording. And that's a very important information to have, and that's where integration steps in and tells you, hey, I know how to do it faster. And the same with area in yellow. If we stay at home, you see the area is lower. The graph of the function is lower, not so steep anymore. The steepness is lower. So then the area will be smaller and number of cases per day will be smaller. Maybe in total it even have the same amount of cases, which is not the case. Definitely less people will be sick if everyone stay at home and stop making other people sick. But say the area is still the same, one is just stretched in time. Still, in this day, the maximum is much lower than in this situation. Then we're gonna have less people filling in the hospitals, and that's how we can decrease number of deaths in the country, because hospitals will be able to handle the amount of cases per day. Now, how to calculate this area over here in blue? How to do it if I don't know the tools? So rectangle was simple. The area of rectangle, we know that. So we know the area of rectangle. That's base times height, right? A times B. Base times height. Simple as that. So what should I do then if I don't have rectangles here? Very interesting engineering idea and mathematical idea is to use whatever you know for stuff you don't know. If we know how to calculate rectangles, can we just create rectangles then? Let's try. So I will create rectangle over here. Then I'll create rectangle over here. Then over here. Then over here like this maybe. Maybe like this, kind of randomly, and like over here. And you see, this area of each rectangle will be easy to calculate. They're just height times base, A times B. They all will have different bases and heights, and it looks okay, right? So there's still gaps, and that's what we're gonna call underestimation and overestimation. But it worked fine, it's doable. And that's the idea, use whatever you know to find something you don't know. And in this case, using rectangles, actually, it's a decent idea. And it's gonna look like this. To approximate the area below the graph, in this case it's parabola, v equals t squared. Again, probably we're working here with speed, v, and t is time. We're gonna approximate using rectangles. And as you can see from left to right, if I'm just using two rectangles, the approximation is pretty bad. Like, what about this empty space and this empty space? What the heck is this? This is like extra sticking out part, too much. So it's underestimation and overestimation. That's using two rectangles. Maybe if we'll use less number of more rectangles, that will make it better. Let's do 4. This tiny one is barely a rectangle, and 4 okay, it looks better. The empty pieces definitely become smaller, and sticking out pieces become smaller. If there's an 8 rectangle, look, the area is basically covered with pink areas of rectangles. That looks even better, and so on. The basic idea is the more the better. In this case, I used 1, 2, 3, 4, 5, 6 rectangles. And I also mentioned they have different bases and different heights, which is possible. So for example, I will do on this example this long rectangle, and then the short one like this, and then maybe like this and like this. It's possible, but then it will be tons of calculations if all of them will have different bases and heights. So the idea that was created behind this thinking is the height definitely will be different because that's how we're fitting the function. All these rectangles have different heights. In this case, they're growing. But let's at least control the base. Let's say that the base is the same. Then at least we don't have to find different bases. If we say that the base is the same, for example, unit 1 or unit 0.5 and so on, we're going to call it delta. This is triangle notation, delta. In this case, delta t. That will be size of the base. If that will be the same, it will be easier to calculate. We have 8 rectangles in this situation, all have the same base, but different heights. Those heights, you see it's touching the function. They will be found from the graph of the function or equation for the function. And that's a pretty cool idea, which I'm going to show you in the animation over here. And this is the idea I'm just explaining you with a delta notation, by the way. And it says that the more the better, as you can see. And the size, the base of the rectangles is shrinking when I add more, right? Because I want to fit more. So in this case, it keeps shrinking. The delta x, which in this case represents how wide each rectangle is shrinking. And then how many do I have? First I have few, then more, 6, 7, 8, 9, 10, and so on and so on. So the more I put, the better the approximation becomes. Now, interesting point of view, how to approximate. I can approximate using left endpoints, right endpoints, and middle endpoints. In those graphs over here, I used middle points. And to do that, I will show it here on the graph. To do that, I will draw the same function 3 times and show you the difference. Because it's very nice to know, to agree basically with people how to approximate the same thing. So from A to B, from A to B, from A to B, I want to find the area. If I'm using left endpoint, then I will start drawing, I will zoom in, a left endpoint rectangle, go to the right and fix the thickness. Go up, touch it with left endpoint, go right. Same base, you see, same base. I will call it delta x, same, delta x, the same. Go up to the right. So my left endpoints keep touching the graph of the function and I'm done when I hit B at the bottom. So you see all my rectangles are touching the function at left endpoints. That's what we're gonna call left endpoint method to approximate the area below the graph. For the right endpoint, I will start still from the left or from the right, doesn't matter. But the idea is to touch with the right endpoint, go outside, go down. Next one, go down. And these delta x's are all the same again. Go down, and go down. So either you try to fit as many as possible, or you are told at the beginning how many we need to use. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So you see I'm being consistent. Seems like I'm dividing interval from A to B into five pieces, delta x's, right? They're all the same, divide by 5. And then midpoint. Midpoint was created from the idea that look what is happening from the first case and the second case. For the first case, you see those gaps? Those are the gaps we're not going to include into calculations. That means our answer will be underestimation, right? Underestimation. estimation. This is maybe the first time we will be doing officially estimation of some calculations with you guys. You thought that mathematics is all only one and right one answer, but when computer science was created, mathematicians stepped in and started helping with approximation for computer scientists. And now it developed to engineering and mathematics and so on. And this is we're going to teach you what does it mean to have estimation of the answer. So you all might have different answers in your homework, plus minus couple decimals. Underestimation here, because we have gaps left. How about for case B? Do you see those sticking out pieces? That's overestimation. So we're definitely going to have overestimation. Well, why it's happening? Because we have too many things sticking out from the left endpoint, or from the right, or under from the right endpoint, or actually vice versa. So let's do midpoint. Midpoint looks like this. Touch the point at A, go to the left, go to the right, and create a rectangle. Next one, and create a rectangle. Next one, and create a rectangle. Next one, and create, actually that's it, rectangle. So here, the middle. Now we have a little bit out and a little bit missing. So this actually usually is the best approximation, because both pieces are tiny and they kind of average out the error. I'm talking about the ERR, error. So this is going to be both underestimation and overestimation, and that's what we're going to call midpoint method. So that was right and point. And this one either mid or middle point method, or just midpoint. So you will see that on the animation over here. This is my left endpoint method. Left endpoint method here, look, it's touching everywhere with the left endpoint and create a lot, many more rectangles. And the more I create, the better the result is. There's almost no empty gaps, and there's almost no overestimation. This is the example of, do you see left or right? It's pretty fast, but you can see it actually. Yes, it is right endpoint method. So the more I do, the better it is. At the end, you barely can see any gaps. That means the approximation will be almost the perfect area under the graph. This is the example where a graph can be located above or below x-axis, and area will be counting as positive and negative. We're going to teach you this later. And finally, this nice animation I wanted to show at the end. If you care and you wash your hands and stay at home, the area goes below that threshold point where the health system capacity can handle the number of sick people in one day. If you don't care, then even though the area might be the same, but in one day we have so many sick people that hospitals cannot handle it anymore. To find these areas, we can use approximation of rectangles, or in the future we're going to teach you that actually you can integrate the function over there that creates that area. That's the idea. Okay, let's keep going. Let me close this. Let's keep going with calculations now. And let's first introduce a couple definitions to move on to the examples. Regular partition, called those same intervals that I'm talking about. Suppose we're working from A to B. That's exactly what I showed you. And then it's a closed interval, and it contains n sub-intervals. Sub-intervals are those little divisions. So I told you we want them all to be the same. And we're going to call them interval from x0 to x1, from x1 to x2, from x2 to x3, and so on till xn minus 1 and xn. It looks like this. From A to B, and the first one will be x sub 0, the last will be x sub n, and then we're going to have this subinterval x1, so from x0 to x1, from x1 to x2, keep going, xn minus 1 to x, and it will cover the whole interval. Then we want to have equal lengths we want to have equal lengths. Delta x is this triangle kind of notation. That's actually a Greek letter, a very common notation for some kind of change in x. We had this actually before, if you remember. And in this case, it will be change in the length of each rectangle. How to find b minus a over n, where a is a starting point and it's x sub 0, b is the end point and it's x sub n, and n is number of subintervals we want to have. So for the first case, it was 1, 2, 3, 4, 5, 6, 7, 8. For this case, it was 8 again, and so on. Subintervals. Then, using these endpoints, x sub 0, x1, x2, xn, of the subintervals, these are called grid points, and they create regular partition of the interval a, b. And in general, you can say that for any x sub k, where k is 0, 1, 2, 3, 4 up until the n, so x can be x0 or maybe x1 and so on. You will have a, that's the starting point, plus k times delta x. And k here is k's grid point. So if I want to say, where is the location of the 8th rectangle? I will take the beginning, the start point A, plus 8 times the width of each rectangle, right? Because I need to have 8 steps away. So I will take the first point and then have 8 steps away to find x sub 8. It may be a little bit confusing right now. Don't be afraid, it's not that bad. When you see the examples, it's actually pretty doable. And that's where we're going to be using Riemann sums. You're going to see them in a moment. And we're going to use left, right, and midpoint Riemann sums, just like I mentioned already, where basically the base is the same. You see, the base is the same, called delta x. And actually in some studies, they don't use the same base, because computer can handle now different bases, but it slows down the process, if be honest. So kind of, it's nice to have the same base, delta x. And the height comes from touching the function. On this particular graph, we're touching the function in the random location. That's what we call f of x star sub k. And then the idea was, you know what, it's not very convenient to have different location. This one is like more to the right, this one is a perfect middle, this one more to the left, middle again. This one over here is like completely on the left, but still not on the left of the rectangle. That's not convenient either. That's why people realized, you know, let's agree on the left, right, and midpoints, and then let's create coding programs out of that. And this is what they called Riemann sums. Suppose f is defined on a closed interval, it's divided into n subintervals of equal length delta x. If x star sub k is any point, so you see a random point. In the case subinterval, case subinterval has a general notation xk minus 1, xk. It can be from 5 to 6 or 10 to 11 and so on. K is keep changing from 1 to n. If you already started coding classes, that's exactly what they're talking in the coding classes. That's basically my counter. That's the thing that's counting. X is counting numbers, 1, 2, 3, and so on. They even call it dummy variable sometimes. Then we're adding base times height, base times height, base times height. Base is always the same. Height, on the other hand, are different. How to find height? Take the point, plug it into the function. It will go over here. Since I have equation for the function, say y equals x squared, I know the height. Here it is. And that's how I'm going to find the area of each rectangle, delta x times f of x. And what kind of x? Some kind of particular x, the point. And we agreed to call those Riemann sums for function f on the closed interval, and we're gonna have left Riemann sums, right Riemann sums and midpoint Riemann sums if I'm using correspondingly left endpoint, right endpoint, or midpoint for the x star sub k. That's the idea. So I think it's pretty interesting, especially taking into account the animation. And I will stop right now and make a smaller video just for the example so that you can go home and do your homework. But don't be afraid of these things. They look pretty theoretical, but actually they're not too bad. And they have a lot of applications, especially in computer science, because for you to know, when we create data, just like data on the patients, we actually do not work with nicely looking functions. We work with literally data points. We work with data points, then we try to connect them somehow. There are literally many methods to connect them. And then the areas below those new functions that we create give you some kind of important information, like distance out of velocity and time, or numbers of patients for the whole year, and so on, many different applications. Finding this area is a challenge. Sometimes we cannot use pure calculus and we need help of machines like computers. And that's where this idea of approximation steps in. Computer knows how to use rectangles and actually has codes given to you. In C++ and Java, you already have codes for midpoint, left endpoint, and right endpoint. You can Google yourself and find all of these. And people literally are paid actually to calculate areas below the graphs using numerical methods. Numerical methods. And the 3 methods we just mentioned to you are part of those methods. See you next time.